So after current, let's start with unit number 3. That's magnetics and magnetism. Magnetics and natural magnetism. Natural magnetism. Magnetics and natural magnetism. So this magnetics and natural magnetism have 2 chapters. This have the first one is magnetics. This is basically chapter number 4 of NCERT. Then it have natural magnetism. This is basically chapter number 5 of NCERT. See the introduction of this chapter. So till now in 12th syllabus, we have studied 2 topics, one electrostatics and another is current electricity. In electrostatics, your charge was at rest. The charge at rest is the source of electric field only. So in chapter number 1 and 2, we studied electric field, different aspects of electric field. But in chapter number 3, your charge starts moving. Once your charge starts moving, you have current. When you have current, then we studied different aspects related to current, but along with current, a phenomena came which is known as magnetism. Magnetism is directly associated to current. So if we talk about sources of magnetic field, then one source could be current carrying wire. That we will study in magnetics. This we will study in magnetics. The next source could be some natural sources like some permanent magnets. The next type of sources could be permanent magnet, or it could be Earth's magnetic field. Earth itself behaves like a magnet. The next could be Earth's magnetic field. There's a current carrying wire, a permanent magnet, or Earth's magnetic field. This we study in magnetics, and this we will study in natural magnetism. This we will study in natural magnetism. So this is the division of the chapter basically. In the chapter number 4, we will study all aspects related to a current carrying wire. And in chapter number 5, basically study the permanent magnet like bar magnet and Earth's magnet. Okay, the whole discussion starts with the concept of magnetic field. So just like electric field, magnetic field is the space around a magnet in which its magnetic properties exist. So magnetic field is simply the space around a magnet. Space around a magnet in which its magnetic properties exist. So the space around a magnet in which its magnetic properties exist is known as magnetic field. When I say magnet, that means source of magnetic field. For me, a wire is a magnet because a wire can generate magnetic field. A revolving electron is a magnet because a revolving electron can generate magnetic field. So that's magnetic field, space around a magnet where its magnetic properties exist. It's just like electrostat. Instead of electric field, I'm just using magnetic. It's a vector quantity. Basically, it's an axial vector. Axial vectors are particularly those vectors which can generate rotational effect. This can generate rotational effect. So we call this as axial vector. Its SI unit is Tesla. Its SI unit is Tesla. Its CGS unit is Gauss. CGS unit is Gauss. So 1 Tesla is 10 raised to the power 4. SI is Tesla, CGS is Gauss. 1 Tesla is 10 raised to the power 4. That's the relation between Tesla and Gauss. Now, when we did electric field in this chapter number 1, we have studied 2 laws to calculate electric field. One was basically Coulomb's law, another one was Gauss law. Just like Coulomb's law, you have one law which is known as Biot-Savart's law to calculate magnetic field. And then like Gauss law, you have one law which is known as Ampere-Circuital law. If you look at the division of the chapter, it's matched with that of the chapter number 1. First, you will learn how to calculate electric field. Then you will see how electric field exert force. This is what we did in first chapter with electric field. Now, in chapter number 4, you will first study the laws to calculate magnetic field. That's basically Biot-Savart's law and Ampere-Circuital law. Then you will learn how magnetic field can exert force. These are 2 parts of this chapter, magnetics. So Biot-Savart's law. So for Biot-Savart's law, it's a well-known fact. If you have a current carrying wire, then that current carrying wire will generate some magnetic field around itself. So if you have a wire carrying current, it's carrying some current ion. And I consider a very small element of the wire. I'm considering this a small element. The length of the element is B. This is a small element. A very small current carrying element. And I want to calculate magnetic field over this one. So this is the position vector R. This angle is theta. This is the angle theta. So you have a small current element. Due to that small current element, you're supposed to calculate the magnetic field at point P. So consider small current carrying element DL or IDL. So for Biot-Savart's law, I'm not considering the whole wire. I'm just considering a small element which is ideal. Obviously, it's a current carrying element. This current carrying element will generate some magnetic field at P. So magnetic field at P, R is position vector of point P with respect to current carrying element DL. With respect to current carrying element DL. So with respect to current carrying element, you are supposed to calculate the magnetic field at. So magnetic field at P. So magnetic field is directly proportional to ideal. It's directly proportional to your current element. It's directly proportional to the sine of angle theta. The angle between the position vector and current element is sine theta. It's inversely proportional to the square of distance between. So the distance between the small current element and the point P is R. So the separation is inversely proportional to square. So if I combine them, then magnetic field is proportional to ideal sine theta over R square. dB is magnetic field. dB is small magnetic field at P due to this theta. Like we represent electric field with E, so we represent magnetic field with B. dB means small magnetic field with small element. When we remove this sign of proportionality, we use a constant. We use a constant K. So it's K ideal sine theta over R square. So this is the expression. In different units, this K have different values. If we consider in SI unit, if I consider SI unit, so just like your electrostat, like in electrostat, this K was 1 over 4 pi epsilon naught. Here this K is mu naught over 4 pi. If I substitute the value of K here, your magnetic field comes out to be, it's mu naught over 4 pi. It's ideal sine theta over R square. And this mu naught is absolute permeability of free space. This is absolute permeability of free space. For different medium, this absolute permeability have absolutely different values. For air, its value is something else. If you take water or any other medium, then it's changed. So this magnetic field, just like electric field, it depends upon medium. If you change medium, then this mu naught will change and your magnetic field will change. So this shows dependency of magnetic field on medium. Magnetic field on medium. So this simply represents the dependency of magnetic field on the medium. If I take mu r is just like dielectric constants. In electrostat, we have dielectric constant. In magnetics, instead of dielectric constant, we have mu r. Mu r, we call this as relative permeability. So if I take relative permeability, then the magnetic field is it's mu naught mu r. It's ideal sine theta over R square. If we take relative permeability, then magnetic field is mu naught mu r, ideal sine theta over R square. That's the relative permeability. For different medium, relative permeability have different values. Okay, just tell me one thing. Have you heard about paramagnetic, diamagnetic and ferromagnetic material? Have you heard about para, dia and ferromagnetic material? Yes. So if you have a diamagnetic material, this is even in chemistry syllabus. If you have a diamagnetic material, for diamagnetic material, your mu r is less than 1. If you have a diamagnetic material, then your relative permeability will be less than 1. But if you have a ferromagnetic material, for a ferromagnetic material, mu r is very, very greater than 1. For example, if you have iron, the order of relative permeability for iron is around 1000. The relative permeability of iron is 1000. This values of diamagnetic and ferromagnetic material means if you take a diamagnetic material, then in diamagnetic material, the strength of magnetic field decrease. But if you take a ferromagnetic material, then in ferromagnetic material, the strength increases. It simply becomes 1000 times. And that increase and decrease is with respect to air. It simply means this is air. In air, I put a wire passing some current I. In air, let's say the strength of magnetic field is B naught. If instead of air, I take iron. In iron, I put the same wire and the same current. At the same point, the magnetic field will become 1000 times. So this is how medium affect your magnetic field. I'm taking same wire, same current. I'm just changing the medium. First of all, the wire is placed in air. Next, the wire is placed in iron. In iron, the magnetic field becomes 1000 times. So that is the significance of relative permeability. The value of mu naught that I am using here, it's a constant. Its value is 4 pi into 10 raised to the power minus 7. It's Tesla meter per ampere. That is the unit of mu naught. And remember, this is for free space. It's air or vacuum. If you change medium, then this value will change.
Sir,
Yes.
what is the difference between mu 0 and mu r?
Mu 0 and mu r, right? Mu r is basically the ratio of mu 0 of medium and mu 0 of free space. This ratio is mu r. This is the dimension full quantity. It have units. This mu r is unitless. Mu r is unitless. It's basically the ratio of. And we usually don't write naught when we talk about any other medium. When you have free space, then we write mu r. So this is the difference. Mu r is the ratio of absolute permeability. So relative permeability is the ratio of absolute permittivity of medium and absolute permittivity of fluids. So that was about SI unit. If you take CGS unit, although your syllabus is in SI unit, you're not supposed to do CGS unit, but just for the sake of your knowledge, in CGS unit, your dB is KIDL sine theta over R square. In CGS unit, your K is 1. So dB is just IDL sine theta over R. So this is your expression in CGS unit. But I will never use CGS unit. We will always use SI unit with the formula is mu naught by 4 pi IDL sine theta by R square. So this is your current element DL. This is the direction of DL. This is your point. The separation between DL and P is R. The angle between them is theta. So the magnetic field due to small element is mu naught by 4 pi IDL sine theta over R square. So magnetic field is a vector quantity. So we can write this term in vector form. If I write this in vector form, so to write this in vector form, I just multiply numerator and denominator by n small r. So it's IDL. I'm multiplying with an r in the numerator and with an r in denominator. So it's mu naught over 4 pi. It's I dl r sine theta over r cube. This dl r sine theta is basically AP sine theta. You can use cross product here in this line. This is basically cross product of dl cross r. So you can write this as dB is mu naught over 4 pi. It's I dl cross r over r cube. This is the magnetic field, mu naught by 4 pi I dl cross r over r cube. This is how we calculate magnetic field. This is the expression of magnetic field in vector form. Now, the advantage of using this vector form is you can, from this vector form, you can calculate the direction of the magnetic field. See, the direction of magnetic field जो है ना, just to express this in terms of dl cross r, just to use vector cross product of vectors. See, dB is a magnetic field. So magnetic field is a vector. A vector can come by the cross product only. So just to write the right hand side in cross product form, I'm using RA. Direction of magnetic field is perpendicular to both dl as well as r. Direction of magnetic field is perpendicular to both. It's perpendicular to dl vector as well as r vector. And is given by, always remember this thing, this is statement. It's perpendicular to both dl as well as r. And is given by right hand thumb. So this is your wire. This is your current carrying wire. This is the point. This is your R. Okay, so can you guess which direction is perpendicular to both? This is your DL. DL is basically the direction of current. What direction is perpendicular to both R as well as DL? Z, right? See, if I take a perpendicular here, then this could be perpendicular to DL, but it's not perpendicular to R. You need a direction. If I take a vector or a direction here, this is perpendicular to R, but it's not perpendicular to DL. You need something which is perpendicular to DL as well as R. So vector which is perpendicular to both DL as well as R is perpendicular to the screen. It's either out of the screen or it's inwards into the screen. So direction which is perpendicular to both DL as well as R is either outwards or it's either inwards. Now, to decide whether it is outwards or inwards, we have to use right hand thumb. One more thing. From now onwards, chapter number 4 and chapter number 6, electromagnetic induction. It's based on directions only. Questions have equal weightage for magnitude and direction. If you can't predict the direction, you cannot calculate the magnitude. So from now onwards, the direction is a major part. So to calculate the direction, there are plenties of laws like Fleming's left hand rule, Fleming's right hand rule. I use just one law, that's right hand thumb rule. Throughout magnetics, okay, throughout magnetics and electromagnetic induction, if we will do the whole thing in the whole discussions, I will never use Fleming's left hand rule or right hand rule. We will always use right hand thumb rule. To see how to use right hand thumb rule. So the right hand thumb rule says right hand thumb. Right hand thumb rule says place your finger along the direction of current and curl it towards the point. Thumb will give direction of magnetic. Thumb will give the direction of magnetic field. Okay, just note it down. Now, the major part is to calculate direction. Now, learn how to calculate direction here. This is your wire, it's carrying current I. This is your DL. The direction of DL is same as that of current. You're supposed to calculate magnetic field. First, draw this diagram in your notebook. Draw this diagram in your notebook. This thing. Okay. Once you have drawn this, take your right hand, not the left hand. Take your right hand. Place your finger in the direction of current. Don't place your finger over the screen. Place your finger over your copy, over your notebook. Take your right hand, place your finger over in the direction of current, and then curl it towards the point. Where is thumb going? Is it going into the notebook or out of the notebook? And I need responses, at least in this particular topic. Response of each one of you. Place your finger in the direction of current, curl it towards the point. Where is your thumb going? Is it going into the notebook or out of the notebook? Or nowhere?
Out.
Out. You are using right or left hand?
Right hand.
Right hand. You have to curl it towards the point. You may be placing it here and just check the pattern in which you are curling your finger. You are curling towards the P or away from P. You just don't have to place your finger along current. First, place your finger along current and then curl it towards the point. Okay, you can make this mistake, right? You can place your finger here and then you are trying to curl it towards the point. It won't curl in this way. So it's better you place your right hand here like this and then curl it towards the point. The thumb will go into the... Fatma, where is thumb? Into the notebook or out of the notebook?
Into the notebook.
Giovanna, now into or out? Inwards we represent by cross. Like into the notebook, you cannot draw that direction on your notebook. So we represent that direction by cross. Cross means inwards. Cross means inwards. Let's take one more case. This is your current I. I'm taking point here. Again, use right hand thumb rule. Place your finger along current and curl it towards the point. Check your finger. Your finger should move towards the point. Do it. And tell me where is thumb going? Into the notebook or out of the notebook? This is outwards. We represent outwards by dot. This dot represents outwards direction, out of the plane of the book. Let's do one more example. This is first example. This is second example. Now, let's say your current is inwards. This is your current. Cross means your current is going into your notebook, and this is your point. Okay, now tell me what's the direction of your thumb. Say, this is the notebook. Okay, this cross means your current is inwards, and this is the point. This is the point. So I'm asking you to place your finger in this way and curl it towards the point. Now tell me where is thumb going. Take your notebook, your right hand, put your finger along the direction of current inwards and then curl it towards P. Now where is the thumb going? This is very
It's
crucial.
going downwards.
It's down. If it's downwards, fine. Downwards is right. If you place it here, you curl it towards P, it's going downwards. This is the direction of art.
Thank you, sir.
So last one. Current is outwards. It's going out of the plane of your copy. I need magnetic field at P. Where is that? What's the direction? Of course, you don't have to worry about your thumb. You just have to worry about the finger and where to curl. This thumb will set according to the direction of magnetic field. Don't worry about the thumb. Just worry about your finger, that you are placing your finger along the current, and worry about curling. Like you have to curl towards the point. Is it upwards? Okay. Yes, yes. Upwards is correct, Joanna. Upwards is correct, right? Upwards. Very good. There are plenty of other laws for this direction. There is one Fleming's left-hand rule, but I'm not using those laws because those laws have limitations. Fleming's can be used if your all vectors are perpendicular to each other, but this you can use in all cases. So let's start with a question on Bart-Savitt's law. Question says that this wire is carrying some current, say a current of 2 ampere. This is origin. Let's say its length is some delta L. This is point P. You're supposed to calculate magnetic field at that's 10 meter. So through the whole system, there's some current I is flowing. So calculate magnetic field. So to solve it, I can use this expression that delta B is, it's mu naught over 4 pi, it's I, it's delta L cross R over R cube. This is the magnetic field, mu naught by 4 pi I delta L cross R over R cube. So the delta B is, I just have to write the all values. Your current is 2 ampere. How much is delta L? 10 raised to the power minus 3. Okay, Afroza, what's the direction of delta L? Delta L. No, it's not downwards. The direction of length is same as that of current. Your current is going to the right hand side. So delta L is going towards positive x-axis. Okay. The direction of length element is same as that of current. If your current is going towards positive x-axis, your delta L is along positive x-axis. And I'm using a unit vector I cap here. How much is R? Fatima, how much is R in this calculation?
10.
10 meter. Direction of R?
G.
Yes, we can use J capital. And your current is 2 amp. I can substitute all values here, right? So yours delta B will be mu naught is 4 pi into 10 raised to the power minus 7 by 4 pi into I. Your current is 2. Delta L cross R. Delta L is 10 raised to the power minus 3 I cap cross R, which is 10 J cap over R cube, which is 10 cube. So 4 pi will cancel this 4 pi. I'm left with 10 raised to the power minus 7 into 2. See this 10 raised to the power minus 3, this 10 are pure number. So pure number can be taken out into 10 over 10 cube, and I'm left with just I cross J. So your delta B is, it's 2 into 10 raised to the power, it's minus 7 minus 3 minus 10, minus 10 and minus plus 1 minus 9 and minus 3 minus 12. I cross J. What is I cross J?
1.
Not 1. I cross J is K. It's K. Delta B is 2 into 10 raised to the power minus 2 K cap. So what is K cap? K cap means along Z axis. Z axis means outwards, positive Z axis. Okay, apply right hand thumb rule here. This is the direction of current, this is point. Outwards, very good. What about the others? Outwards, very good. Just place your finger along the current and curl it towards the point. Your thumb is going outwards. So that is the direction of magnetic field, it's outwards. So that's your magnetic field, which is outwards. This much of Tesla. And if you, yes, outwards. So if anyone of you doesn't remember why I cross J is K, just remember this thing. Right, IJK, if you move clockwise, like if you do I cross J, it's K. J cross K will be I, K cross I will be J. If you take anti-clockwise, then this is negative. Here, clockwise is positive. If you take anti-clockwise, this is negative. Remember this thing for further numericals. Clear?
So why did we use the vector equation here?
That's your choice. Instead of vector equation, we can also use scalar form like ideal sine theta by r square. But I just want to show you that using vector equation, you can calculate the directions without even right-hand thumb rule. And then after right-hand thumb rule, you can just compare your result. Okay, while using this expression, mu naught over 4 pi ideal sine theta over r square. Now, if you are getting j cap, then using right hand thumb rule, it should be upwards because j cap is upwards. Outwards is it k cap. If you're getting j cap, then your direction should be like this. If you're getting minus j cap, then this should be like this. So while using this expression mu naught by 4 pi ideal sine theta by r square, always remember while using this relation that this is valid for small current element. Small current elements. It's just like Coulomb's law. Coulomb's law was valid for a point charge, for a small current element ideal. You cannot use this Biot-Savart's law directly for a long wire. If I say that this is my wire, it's carrying some current I, you cannot use Biot-Savart's law for the complete wire. You will use it for a small current element only. So the question says express Biot-Savart's law in terms of current density. You can express your Biot-Savart's law in terms of current density. J. So your magnetic field dB is its mu naught over 4 pi. It's ideal cross R over R cube. Instead of I, you can just write J into A. Your current density J is I by A. Your I is just J into A. If I substitute these values here, your magnetic field comes out to be its mu naught over 4 pi. Your I is J into A. It's dl cross R over R cube. This A into dl, area into length is volume. Area into length is dV, basically volume. So this could be written as that your magnetic field is. Now see, volume is a scalar quantity. I can't keep volume inside. So I have to take volume outside, but current density is a vector quantity. So I just write this as J cross R over R cube. These are some simple conceptual questions. This is how you can express your current density in terms of your Biot-Savart's law in terms of current density. Do one more thing. Express Biot-Savart's law in terms of charge and their velocity. In terms of charge and their velocity. Solve it. You can use this expression that I is dq over dt. This is your Bart's law. V naught over 4 pi. It's I dl cross r over rq. How much is I? If I substitute I as dq over dt here, your magnetic field comes out to be mu naught by 4 pi. It's dq over dt dl cross r over rq. See, this dl over dt is velocity, na? This is velocity. Substitute v instead of dl over dt. So your magnetic field comes out to be, it's mu naught over 4 pi, it's dq, it's v cross r over rq. These are very common conceptual questions on Bart's law.